So let's welcome Lilinoe on stage with the talk Python-driven robotics, where Bytes meet Biopsies. Let's please give a round of applause. Thank you.
So good afternoon. My name is Lilinoe Harbottle. My talk is Python-driven robotics, where Bytes meet Biopsies. Today's date is July 24th, 2025. So if you're looking at this a year from now, some of this might have improved. And this is PyCon Portugal 2025. So welcome, everyone. So let's start with a thought experiment. I want you to silently in your head think about if you know anyone in your circle of friends, in your family, neighbor, coworker who has ever been impacted by cancer. Just think for a second. And then think, do you know anyone who's impacted by lung cancer? So the whole idea behind this thought experiment is that it's a problem that is affecting everyone in the world. So just in Portugal alone, out of all the cancer deaths, lung cancer accounts for about 11.66%. I checked at different sources, the DGS, GECP, INE. They have several different estimates for these numbers because there are different ways of reporting this data. Also, since 2020, a lot of data has been hard to track because of COVID, as well as a lot of different hospitals have methodologies that are slightly different when they report these numbers. So this estimate is ballpark. Just to give a short comparison, the World Health Organization believes that about 1 in every 5 cancer deaths around the world are due to lung cancer. And this number here is just for Portugal alone. So what do those numbers look like? Again, the estimates are ballpark. Within Portugal, about 3,000 malignant lung cancer diagnoses are found every year. Globally, about 2.4 million new lung cancer cases are found worldwide. And that's an estimate because not all cases are diagnosed pathologically by looking at the cell. Some are too dangerous to diagnose, so depending on the doctor's preference. Again, these are estimates because every country, every hospital has a different methodology. And just within Portugal alone, out of all the lung cancer diagnoses, about somewhere between 70 to 80% are sort of caught too late, and that's a problem. Usually with cancer, the earlier it's found, the better. The better chances of survival for the patient, the better the treatment, the more options available. There are many reporting agencies listed here. They have a lot of wonderful advice, documentation, infographics about how to understand this, how to detect, what to look for. I encourage you to check. All these resources are updated very frequently, sometimes quarterly. So we talked about a problem. What does this market look like? There are different market research reports that think around 29 million in revenue is will be the global market for robotics by 2032. That is a very conservative estimate. Some market research say it's somewhere in the 50 billion range. This is the more conservative number, but in the next few years, surgeries will look a little different. You see this image, we'll go back to that, trying to figure out what does that have to do with this talk. We'll revisit it. So, beyond these numbers, beyond the diagnosis, what can we do to support doctors? Or what have we already started doing as a software community? That's the question. So today, we already talked a little bit about why we're having this talk. We'll go through a few key concepts, and then we'll go through a detailed case example. And the idea is that to give you a starting point to come up with new questions, new ideas, and maybe solve this global problem. So, concepts. And I'll let you know, this is the short list of terms that I wanted to introduce. I had a longer list, but we'll start with the most important ones. So if you decide to go on the internet and search on your own, you'll have the base foundation to go and explore on your own. So lung nodule. It's a small abnormal spot on the lung, usually found through a CT scan. So put yourself in this case. Pretend you go to the doctor because you have this weird pain in your chest or you have a cough that just won't go away and you don't know what it is. The doctor will usually recommend a scan. A CT scan is similar to an X-ray scan, except it's multiple angles, multiple slices, so that you get a complete picture of the lungs. So lung nodule, it's an abnormal spot. When doctors find this, they don't know if it's going to be benign or malignant. They just know it's something there when they look at the scans. We already talked about CT scans, medical imaging. There are different types of medical imaging techniques out there. This is just one of many. This is slightly more modern. I know people have heard about, MRIs. That's more expensive. That's magnetic resonance. Definitely viable option as well. It depends on the doctor and what they feel is safest for the patient. Okay, more terms. All right, so we talk about robots, we talk about medicine. Where does it all come together? So recently, the new term, or not new, depending on your perspective, minimally invasive surgeries are surgeries that can be performed through smaller incisions than traditionally done. Back in the day, we used to think, okay, you go to the doctor, you go to the surgeon, they have to cut you open, then they stitch you back up, and then you take weeks in the hospital to recover, and that's dangerous. You spend a lot of time out from work, people have to take care of you, that's a huge hospital bill. So that's very expensive. What is the difference then when we say minimally invasive? That term is, obviously something a lot of hospitals and surgeons are using now, or the idea is that they can make a smaller cut or maybe no cut at all. That's where we're going to get to. So it's been around for a while, minimally invasive surgeries, or you'll look it up, it's MIS. My area that I'm able to focus on right now, because there's so many different types of cancers, so many different types of surgeries, is bronchoscopy, lung cancer. So bronchoscopy is a procedure where a thin tube is inserted down the airway. Has anyone seen the movies where they see the person sitting in the hospital and they have this mask on them and it looks really uncomfortable? I've seen that and I'm like, I can't imagine. Well, the bronchoscope is smaller than that. Think about as thin as a pencil, thinner, and it goes down the trachea. So when a patient goes in for this type of operation, they're usually put to sleep. And then lastly, robotic-assisted surgery. So the idea is not that the robot will replace the surgeon. We're not there. The idea is that the robot will give the surgeon almost like super surgeon powers, kind of like Iron Man, if you think about it, right? Except they don't have the cool suit. That would be more expensive. But it's the same idea, making these surgeons and doctors super doctors. Okay, so we talked about some terms. Now we're going to go a little bit more into where does Python fit into all of this? Some of the areas that we might not have time to get into today because there's a lot of content. Lung nodule detection, visualizations, and in the future, robot guidance. Okay, so we're going to briefly go over some of the models, and none of these are brand new. This is just one of the many ways that I would approach it if I were going to build a prototype today. And I apologize, I didn't even mention I'm a data scientist. So I like looking at data. There's so many amazing libraries out there. These are some of the tools that I have used. Everyone else has probably seen TensorFlow PyTorch. Amazing for CNN. Training data is publicly available from a lot of different hospitals and government agencies. I use DCIA. There's Luna 16 as well. Some of the publicly available data can take days to process. For example, I was trying to process about 200 gigabytes of data. I absolutely needed to use the cloud VM for that. It took a while, so even then. And then the whole idea is that there are different models out there. They are constantly evolving. So again, a year from now, this list of my favorites will look different. And if we're wondering what that thing is on the left, that is a bronchoscope. It's blue, and it is guided by a tension wire. So it's not a robot arm like Iron Man. Unfortunately, the tension wire is inside the blue. And so that light on the end contains a camera, a light, and depending on the model and the type, something to take a sample of the tissue. Every company has a slightly different scope. The lengths vary for adult and different age groups. So. Also, before we go back into the technical, this is a 3D rendering based on MRI and CT scans of the patient lungs. And I also want you to keep in mind that not all hospitals are connected to the internet. So when you think about, okay, you're gonna have a robot in a hospital, how is it gonna process all that data? It needs to be in a closed system. Your robot needs to be reliable because your software release is not gonna be every 2 weeks. It might be once every year, year and a half. So your software code needs to be tested both in-house, by third parties, and by doctors, by clinicians, before it's released to the public to make sure that it is absolutely safe. But this is one of the many models that uses multiple algorithms. I think we've been using what we call AI for years. We called it algorithms back in the day. But this is one of many ways. And in this image, you can see on the right, those are DICOM images, so CT scans. They're just different types of slices, different views that a doctor would typically look at when they're doing an operation. So the idea is that when I said super doctor, I really meant it. They have the ability to see not just the scans, but on the same screen, a 3D rendering. And if you see that lighted blue path, where the area in question is, so that when they actually do guide their scope down through the airways for each patient who has a unique set of lungs, they have a little bit more help than if they were just to do it the traditional way. Okay, so let's go back. Okay, so I mentioned I'm a data scientist. When you think about a lot of these medical scans, it's a massive amount of data. And what you also want to understand is that because each patient is unique, whenever the robot software is fed all of these unique images for a particular patient, there are a lot of standards, and one of the standards is called DICOM, which is an international standard for how medical images are stored today. Again, that could change in the future. With any data scientist, there's always a process of cleaning, processing, normalizing data. Some of the libraries that I have used are listed, and there are different ways for inputting and transforming the data into viable models. So here's a quick snippet. This is nothing new. This is one of many ways the ways I would approach it. And this is for a cloud environment. I mentioned providing a prototype for just the demo purposes. And I just wanted to show examples of DICOM images or CT images for a lung. So imagine you have hundreds of these for a patient. And these are all reliable medical files that have gone through, passed through all of the DICOMs, the hospital systems. You can actually take this and use it to train and create the 3D rendering for a doctor. There are a lot of steps, and doctors often have to go through a lot of in-house training before they use the robot, but the idea is that once they are able to load in the images, boom, they get their 3D image when they're ready to go do their operation. And this is just for demo purposes, using Google Cloud to load in the data. Obviously, because of the way the hospitals are organized, not everything is uploaded to the cloud. So whatever is available is upon the generous, agreements with hospitals they have with institutions that do academic research on this. So I've been asked before, so how do we take care of the fact that, what if all the data is for men and the model isn't trained on women? Unfortunately, because of the way that personal identification is removed from hospital files, there's no way of saying, oh, well, this data set has 100% women that we were trained on. Like, that's not available. But that is an area for future consideration, especially because the patients aren't all from one group or one region or one height or whatnot. So there is always room for improvement, but this is just the model that is based on what is publicly available today. I also have a really simplified, very, very simplified architecture here. Normally, you would have multiple iterations of the convolutional layer and pooling layer, probably in the hundreds. So this is really oversimplified. The idea is that, how would we predict cases if we had all these images? That is the question. So TensorFlow and PyTorch are extremely powerful in this case. And as I mentioned before, these methodologies could change in the future, and hopefully they will improve and get slightly more efficient, because this type of analysis takes quite a long time to process. So my hope is a year from now, someone will come up with something better. Maybe someone in this room. Okay. In addition to that, there are different training, validation, and metrics alongside a lot of the analysis. These are just a few. I won't go into detail because I know that these are also highly subjective based on the type of data that we're processing as well and what we have available. And finally, we're getting to the example. But finally, we're going to talk about visualizations. So I already briefly skimmed over the 3D rendering, the different types of slices the doctors would potentially look at when they're doing an operation. And this 3D reconstruction, this is new. This is not something that has traditionally been used in surgeries, and it makes a doctor's job even easier. So if you think about what we talked about, minimally invasive surgeries, instead of an operation taking hours and recovering taking weeks, you could hypothetically have a patient walk in the morning, have an operation that lasts 20 minutes, and they could walk out that same afternoon and go back to their lives because they have no incision into the human body. So that reduces the costs for that patient. It also frees up the hospital bed for someone who could really use it. So when we talk about what is all of this for, it's for helping the doctor and help them make their decisions and improve the chances for the patient. And of course, we have a lot of libraries. Data scientists here might recognize some of these. These are some of the libraries just that a data scientist would use. If you talk to someone in instruments, controls, systems, hardware, they're going to have a completely different set of libraries. But when you think about a robot, of course, it's going to have millions of lines of code. You're going to have a mixture of open source libraries and custom built. Okay, let's get to an actual example here. So this is one of many examples out there of what a robot could look like. Some people might have seen the type of robots that have like multiple arms. It looks like an octopus. This is just a different model. And we'll go into a little bit more into detail about this one. Okay, so I mentioned the blue thing. That's the bronchoscope. That is the most important part because that actually goes into the human body. And then we have the cart. So the cart has the arms. Notice this particular cart has 2 arms. We'll talk about multiple arms in the future. But the bronchoscope is on the attachment, as you can see here. And that attachment also has saline air instrument insertion and the like. And then the tower. The tower is the brains of the robot. That contains the power and the code. And then, has anyone played with PlayStation before? Does that look familiar? Yes, exactly. The idea is that for a surgeon to pick up a controller, it should be as sensitive, as intuitive as almost like a flight simulator. So when they are trained on these types of models, it should be something that is not so foreign that it's hard for them to pick up. And they go through a lot of training. Okay. So this is thankfully to the Mayo Clinic, this is a computer-generated image of the scope inside the lung. That funny shaped thing in the middle is could be a benign or malignant tumor. The top left is what the camera would look like as it's traveling through the different airways. And then on the bottom, you can see the yellow and green. It's a 3D model of what that potential area would look like. And the point is guiding the doctor to that particular spot. So it's like pinpointing the target. The doctor has full control, but they also have helpers to figure out, am I getting too close to the lung wall? Is my navigation good? These things are supposed to help the doctor and improve the patient's chances. Okay, so let's recap an example. We talked about minimally invasive. So the idea is that, yes, in theory, if a doctor doesn't need to make a cut into the human body, that is minimally invasive. So if the scope travels down the trachea, takes a sample of the tumor, and then extracts it, or possibly breaks it up and sucks it out, that's an operation that would be considered minimally invasive. This real-time visualization is supposed to improve chances for the patient. And also, the idea is about improving precision so that there are, fewer unexpected incidents, as well as allowing the doctor to really analyze the patient's medical files before the operation. As soon as they preload it, they can analyze these files and look at these 3D renderings and then make decisions and then go into the operation. So there is a lot of prep time for the surgeon, but they were going to prep anyway, right? This just made it a little bit more efficient. And this is robotic-assisted surgery. There are so many challenges with these types of robots. As you can imagine, software is what unites all the different pieces and the different moving parts, from hardware systems, integration, QA, clinical instruments and accessories, robotics and controls. Software unites all of it, but with any product, there's always going to be room for more improvement. There's always going to be asked for more features. Obviously, better data, more robust models as we improve our algorithms, better integration with hospitals, more adaptive robotic controls, improved architectures, and more trust building. And I mentioned future architectures because when you think about any one of these robots, it will take several billions of dollars and at least 7 years for something to get from concept to out to the patient because of all the testing and all the government controls as to what is safe for patients and all the different types of ways that things need to be checked before it goes in human. So a lot of the process is, architectures are evolving, systems are evolving constantly. So thank you for your time. I think we have a few minutes if anyone has questions, and I'm happy to chat afterwards if everyone just wants to go to lunch. If we want to talk about, different robots, companies that are offering this out in the world, and where Python can improve this community.
Thank you for your talk. We have some minutes before lunch. I'm sure you're all very hungry by now. Any questions?
Thanks for your talk. It was lovely, very human, and I think it resonates with all of us. And now, in a kind of mid-tone between the seriousness of it and the important playful aspects of human development, the question is this. So you showed us a probe that goes into the lung for a minimally invasive procedure, lovely, and the idea, and you played with it, of a PlayStation-like controller, which is familiar. Now, one thing that PlayStation controllers do, and I've never played one, okay, for the record, is that they feed you back when you bump into walls, right? If you go into a car, then it kind of rumbles or something. Would that joystick help the surgeon say, don't push because you're going too far into the lung? Would it rumble back? That's the question.
I love this question. Thank you. So you're asking about haptic feedback. I can say yes, there is a company out there that is already developing that. Unfortunately, that's not where I worked in. I am so jealous. I wish I could. Absolutely wish I could have been on that project. It is very much something that's coming up. And as you can imagine, even that feature would need to go through a lot of government approvals. Just because I think it's not if we want to build it, it's can we build it, because will it get approved?
Sure.
That's the main challenge. But yes.
Thank you.
So thank you again for your great talk.